Welcome to the Peacademia course on the basics of semiconductors. This lecture covers the minority and majority charge carriers in doped or extrinsic semiconductors. Let's start. By the time you finish this lesson, you will learn the majority charge carrier concentration, minority charge carrier concentration, and the side-by-side energy band diagrams of P and N-type semiconductors. Now that I have covered the intrinsic and extrinsic semiconductors and the Fermi level and function concepts, it is a good idea to dedicate this lecture to the majority and minority charge carriers in doped semiconductors. Note that by saying doped semiconductors, I mean extrinsic semiconductors. I start from an N-type doped silicon semiconductor, and then I cover P-type doped silicon. Here is an N-type doped silicon bulk. Just as a reminder, the concentration of silicon atoms in general is 5 times 10 to the power of 22 per centimeter cube. At room temperature, we already calculated the intrinsic charge carrier concentrations for both the electrons and holes. They are 1 time 10 to the power of 10 per centimeter cube. As I already outlined in the previous lectures, we can control the electrical properties such as conductivity of semiconductors by doping impurities. For example, for silicon, we can use phosphorus as a dopant to create an N-type silicon semiconductor. Phosphorus for silicon is a donor since it donates free electrons to the semiconductor. As a result, the concentration of free electrons is no longer equal to the concentration of holes. Normally, the concentration of donors, Nd, is in order of 10 to the power of 14 to 10 to the power of 20 per centimeter cube. In the case that the donor concentration is close to the higher end of the spectrum, 10 to the power of 20, we say the semiconductor is heavily doped. We usually use the heavily doped semiconductors for ohmic contacts. If the ionization energy is not that big, we could say that all the donor atoms donate 1 free electron at room temperature. Even if we take the lower end of the donor concentration, 10 to the power of 14, this number is much larger than Ni. As a result, since the concentration of free electrons in an N-type semiconductor equals Ni plus Nd, and Nd is much larger than Ni, I can confidently say that the free electron concentration is Nd, 10 to the power of 14 per centimeter cube. In an N-type semiconductor, the whole concentration remains intact and equals Pi. In an N-type semiconductor, since free electrons outnumber the holes, they are called majority charge carriers. Holes are minority charge carriers. Here is a P-type doped silicon bulk. Again, the intrinsic charge carrier concentration at the room temperature is 10 to the power of 10 per centimeter cube. In a P-type silicon, the concentration of acceptors is generally between 10 to the power of 14 per centimeter cube to 10 to the power of 20 per centimeter cube. As long as the ionization energy is not that big, at room temperature, the concentration of holes, which is Pi plus Na, is almost equal Na. This is because Na is much larger than the intrinsic concentration Pi. In a P-type semiconductor, the free electron concentration remains intact and equals Ni. So in a P-type semiconductor, the majority charge carriers are holes and minority charge carriers are free electrons. Now, imagine I have two semiconductors. One is P-type, another N-type. Consider that they have no electrical connection. What I want to do now is to draw their energy band diagrams and compare them with each other. To do so, I first draw an imaginary Fermi level. This is my reference level to draw the rest of the energy levels. For a P-type semiconductor, we already know that EF is close to the top of the valence band EV. Here is EC for the P semiconductor with a distance of Eg from EV. The intrinsic Fermi level EI is almost in the middle of the energy gap. Now, let's work on the N-type semiconductor. In an N-type semiconductor, the Fermi level is close to the bottom of the conduction band EC. EV is below EC with a distance of EG. The intrinsic Fermi level sits almost in the middle of the energy gap. As long as the P and N-type semiconductors are not connected, or in other words, do not make a P-N junction, the energy band diagrams remain intact. In this lecture, I covered the majority and minority charge carrier concentration in doped semiconductors and also side-by-side energy band diagrams. In the next lecture, I will discuss the P-N junction diffusion and drift processes. Thanks for joining this lecture of Peacademia.